Hello friends, so we'll see today the collision theory of unimolecular reaction. So previously in previous lecture we have seen that through collision theory we have derived this rate constant is equal to P into ZAB e to the power minus EA upon RT, and from Arrhenius equation K is equal to A into e to the power minus EA upon RT. So this is the Arrhenius equation and this is the equation derived from the collision theory. So what is A? A is called as the frequency factor or pre-exponential factor. So now we'll see this Korean theory for unimolecular reaction. It is given by the Lindemann hypothesis. So a unimolecular reaction in general means A is converted into product. That is, in such a reactions, only one molecule of the reactant take part in the reactions. So consequently, question arises: how do molecules in a unimolecular reaction attain their energy of activation? So again, Lindemann gave this answer that the behavior of the unimolecular reactions can be explained on basis of the reactions during this time. The activated molecules may either react or it may be deactivated to ordinary molecules. It may react or it may be deactivated to ordinary molecules, and consequently the rate of reaction will not be proportional to all the molecules activated but only to those which remain active. We can see this through this illustration. Suppose this is a molecules A and B, unimolecular, and under equilibrium it is converting into A star. So A star is the activated molecules. It can go back also, it can go front also. Front means can convert into product. So when they convert into product, this is the K3. So K1, K2 and K3, these are the rate constant of different process. So this is the unimolecular of Lindemann hypothesis. Now we will see why this collision theory, what are the weakness of this collision theory. Failure we have seen it. So what are the weak points in collision theory? So following are the reasons for the weakness of collision theory. So collision theory is totally based on the classical mechanics. Classical mechanics is very crude and it requires modification. What is the meaning of very crude? Very crude means it is applicable to simple gaseous only, and also for the solution of simple molecules, not for the complex molecules. Mathematical calculation of this theory, these are based on the assumption that molecules are elastic hard spheres. This we have to assume it. Such assumption is true only in ideal gases. In point number 3, in the calculation for energy of activation, only translational energy has been considered. No account is taken for the internal motion of reacting molecules. That is, it ignores the vibrational and rotational energy of molecules. So this energy has not been taken into account. Fourth one, it does not consider the energy changes take place during the breaking and formation of bonds. So for the above reasons, the correct theoretical predictions for reaction rate are difficult in the case of reaction with large and complex molecules. Hence, from the above fact, it follows that a simple collision theory, this is the case of oversimplification which needs modification. It requires modification. Therefore, a modern theory known as transition state theory, it has replaced the older collision theory. So now we will see what is transition theory. So it is also called as activated complex theory, and it was first proposed by Pelger and Minger in 1932, and later it was developed by Eyring and collaborators in 1935, and this is also called as absolute reaction rate theory. We can also call this absolute reaction rate theory. Why? Because it uses fundamental physical properties such as dimension, vibrational frequencies, masses, etc. of the reactive molecule to calculate the rate of chemical reactions. So in this theory, details of collision process are not considered. It is based upon the following fundamental postulates. We will see those postulates. It is believed that the reactant molecules, it will come closer and it will first transform into the intermediate energy rich compound called activated complex or transition state. So this is the intermediate energy, that is activated complex or transition. This is the first point. Second postulate, the energy in activated complex is higher than that of reacting molecules. So it may be formed by some loose association or bonding of reacted molecules with necessary rearrangement of valence bonds and energies. If it is unimolecular reactions, then activated complex may be produced by rearrangement of atoms of redistribution of energy. So it is for this reason that the theory is called as transition state theory. Next point, the activated complex is in equilibrium with the reacting molecules. However, the product may or may not be in equilibrium with the activated complex. So the third point, it may or may not be equilibrium with the activated complex. In any case, the activated complex, though unstable, the activated is unstable, it has a transient existence, is treated formally as a definite molecule. So this is a definite molecule with an independent entity. The activated molecule or complex subsequently breaks up to produce the resultant in a definite rate. So it has one definite rate and it will give the result. So result, this is reactant molecules, it converted into first activated complex, and this activated complex is converted into product. So this can go backward also, this can go forward also. And this is unstable with respect to a special mode of vibration which leads to its dissociation into products. The special mode of vibration, in fact, it gets converted into translational degree of freedom and along the action of reaction coordinate, which leads to the breaking of bonds. That is, in addition to having 3 translational degree of freedom, it has the 4th degree of freedom along the reaction coordinates, and this 4th degree of freedom which finally converted into product. So this 4th degree of freedom nothing but the activated complex. So let us see through this illustrated examples. We will understand this concept. So I have taken example of dissociation of hydrogen iodide, and again this whole reaction can give exothermic or endothermic reaction. So this dissociation of hydrogen iodide is an endothermic reaction. So we will see HI is converted to H2 plus I2. So this is the HI molecule. So first these 2 HI molecules, this is HI, and again they are forming this breaking and the formation of bonds. Dotted line you can see that. So in this here the bond length is 0.74 angstrom, its bond length is 0.74 angstrom, but this bond length is 2.95 angstrom. This is stretching. It is happening in activated complex, and we can see the 4th degree of freedom. So it can be this bond can be partially ruptured. Initially bond is this one, so now this bond is breaking, this bond is formation take place. After formation, we can see the bond is 1.64 angstrom, this is 1.6 angstrom, and this molecule is formed. So rate of formation of product, it depends upon the rate of decomposition of the activated complex. Let us consider reactions of 2 reactant A and B. So this is A and B reactant, and it is converted into activated complex, that is AB star, and this activated with this rate constant converted into product. So we will derive one mathematical relation with this hypothetical reaction. Let us see how. So this is the reaction. So now I have drawn this some reaction coordinate diagram based on this reaction. So we can see this reaction is a activated compound. So this is endothermic reaction and this is the exothermic reaction. So that we will see one by one. So for endothermic reaction, so this is a reactant. Reactant means molecule we have A plus B. So this is the initially A plus B, and this activated complex is XAB. So we can write here AB, and this is your star, and finally we are getting the product. So this is our product. So in this way we can see this is going like this one. This is the activation energy of reactant, this is activation energy of the product, and this whole is the activation energy. This is the threshold energy. The whole from this point to this point is the threshold energy. So threshold energy minus activation energy is the energy of the reactant will give you activation energy of the reactant. And in this case, heat of reaction is positive, means energy of whole this minus this, or because if whole this minus this will give you the energy of the product. Now in this above diagram you can see in the same way we can see this is the reactant is up, energy of the reactant is more than the energy of the product. So this in this case delta H is negative, in this case delta H is positive. This is an exothermic reaction, this is the endothermic reaction. So in the above diagram there is a small initial fall in the potential energy of the reactant. You can see this energy of the reactant is falling, which is due to the approaching of the reactant molecules close to one another before reacting to yield the activated complex. Similarly, there is a small final rise in the energy of the product. We can see it is rising of the product. Why? Which is due to the falling apart of the molecules after the reaction. So be careful in drawing the diagram properly. Let us consider bimolecular reaction between a molecule A and B. So let us see the mechanism. A plus B, already we have seen A K1 by K2 and giving AB, and product is giving this one. So here AB activated, AB nothing but it is a activated complex, and its concentration will be calculated by means of simple statistical mechanics. So we will use this mechanics. We know earlier that rate of reaction is nothing but the rate of decomposition of the activated complex. We already studied this thing in starting lectures. So rate of reaction is nothing but frequency of the crossing of energy barrier multiplied by concentration of the activated complex at the top of energy barrier into probability of the crossing the barrier from the collision theory, that is per unit time. So this we have already discussed in the previous lecture. Now we will see how we can calculate the rate of formation of transition state. The existence of transition state, it has been shown experimentally by Ahmad Zewail. So actually the transition state is the configuration of atoms in the activated complex, and if attained leads to formation of product after frequency. So mathematically this transition state can be derived that rate of formation of product is equal to RT by Avogadro number into H. So this is the calculation came from the kinetic theory of gases. So no need of deriving this equation, just learned by heart. Or if you take R by Na, so R by Na is nothing but this is called as the Boltzmann constant, that is the Kb. So Kb is the Boltzmann constant. So we can write whole this equation into Kb into T upon H, R by N into T upon H. So now equilibrium constant for the equilibrium established between the reactant molecule and the X star is K star. That is when reactant is converted into activated complex. So we can write the rate constant of the reaction K is nothing but the Kb by H into T, Kb into T by H into K star. So this is the rate constant of the reaction irrespective of its molecularity order. So it will becomes your RT upon, or you can if you take Kb into R by Na, T by H into K. So these orders both are same. And what is K naught? K naught is the equilibrium constant which is achieved between the reactant molecules and the activated complex. This we have already seen in the rate order of the reaction, how we can calculate this these equations. So K star is X star into A into B. So why we writing? So since we have seen that K A plus B is giving you A plus B complex, and finally this will give you your product. This is the K1 and K2. This will give you your K star. Okay, K star means this is your K. So if you calculate first this reaction, then this reaction, so we will get this K star. So now from thermodynamics we know that delta G star is equal to minus RT natural log of K star. So delta G star is nothing but the gives free energy when an activated complex is formed, that is this thing. So we can write that natural log K star is minus delta G star upon RT, or we can write in this form K star is equal to e to the power minus G star upon RT. So now you put this value in equation 1, means in this equation this K star value you put whole value. So if you put the whole value, you will get this equation Kb into T upon H into e to the power minus delta G star by RT. And what is delta G? So delta G from thermodynamics, delta H minus T delta S. Delta H is change in enthalpy of activation, and this is the entropy of activation. This is the entropy of activation, this is the enthalpy of activation. Now we just rearrange it. This is the rate constant equal to Kb into T by H, and this we can write it delta H minus T delta S star divided by RT. So just rearranging, if you rearranging, you will get Kb into T upon H, and this is the e to the power delta S star upon R, e to the power minus delta H star upon R, or we can write in this form also. So this whole equation is called as the Eyring equation. So from transition state theory, this equation we get, this station includes the delta S, and this equation is called as the Eyring equation. What is the significance of this equation? So we will see this equation in transition state theory. So this Eyring equation is, this is nothing, you can see both are same. So this Eyring equation consists of two factors. One is this factor, one is this factor. The first factor and second factor is there. So what is first factor? First factor is constant at constant temperature. So this factor is constant at constant temperature. So hence rate of reaction depends only upon the second factor. The second factor involves the delta G star. The delta G star is nothing but the delta S star minus T delta S star. with a negative sign. So this means that at a particular temperature, greater the value of the free energy of activation for a reaction, the slower will be the reaction. This will indicates. Now compare the this is with the Arrhenius equation. So if you compare with the Arrhenius equation, this is Arrhenius equation. So you will observe that frequency, that is a pre-exponential factor, is the value of this one. Since delta EA activation energy is equal to delta H star, so this is the equal. So you will get the pre-exponential factor. This is the value. Now if you compare with the collision theory equation, then whole this into this. This is the collision theory equation. So we observe that so P into Z is equal to this value. Thus probability factor P is related to the entropy of activation, that is delta S star, and Z is called as the role of encounter, that is equal to RT upon Avogadro number into H, and delta E is equal to delta H. So we can compare like this thing. Now what is the advantage of transition state theory over the collision theory? So in collision theory, the correction factor P was introduced arbitrarily, whereas the transition theory, its inclusion has been justified. Here we have actually introduced, but here it is justified in terms of entropy of activation. This is the one major advantage by using the transition state theory. The concept of the formation of an activated complex seems to be more appropriate than the assuming that the molecule just collide together and change into product. So this concept seems to be more appropriate. Why? Because in the collision theory, molecule just collide and change into product, but activated complex will give you more appropriate concept than this concept. Kinetic stability of fuels. So there are many fuels which are unusually stable, even in presence of oxygen or air. So they are unusually stable in presence of oxygen. It can be again explained by the concept of activation energy. So in general, what happens? The activation energy of the combustion reaction is quite high. Activation energy of any combustion reaction is very high. When a flame is applied to the mixture of fuel and the air, the contents near the flames are raised to high temperature. The contents near the flame raised to high temperature. Then the supplied energy is enough. There is such a enough quantity to cause the combustion of a portion of fuel in oxygen. The heat liberated by the combustion, it increases the temperature of the remaining fuel, and flame once produced is sustained. It burns continuously. Thus we realize that many reactions which are feasible from the consideration of free energy may be prevented from occurring. Why? Because of high activation energy barriers, and such energy barriers are blissful for the existence of life on earth, because they provide stability to the reactant like fuels or contents or explosive in bombs, etc., which are otherwise unstable from the point of view of thermodynamics. And this leads us to make a concluding statement that reactants which are thermodynamically unstable at ordinary temperature may not be kinetically unstable.